Hey everyone, and welcome. Today, we are diving into one of the most fundamental shifts happening in computing right now. We're talking about the engine that's going to power the next wave of AI, and it involves a leap from the speed of electricity to the speed of light.
First, just look at this number, roughly $1 trillion. Let that sink in for a second. That's not some abstract economic forecast. It's the projected size of a single industry, and it's all being driven by one massive, world-changing force.
So, that trillion-dollar figure, that's where the semiconductor market is headed. And this chart makes it crystal clear that AI is the rocket fuel. You can see it everywhere. AI PCs, data centers, robotics, it's all on this explosive growth curve. But here's the problem. This incredible boom in AI creates a huge, massive data traffic jam right down at the microscopic level, inside the chips themselves.
We are, for all intents and purposes, hitting a wall. Modern AI models are unbelievably hungry for data, and they need to move just oceans of it between different chips. And the old-school copper wires we've been using for decades, they're just running out of steam. They get hot, they burn a ton of power, and they just can't keep up anymore.
So this is the trillion-dollar question, right? How do you solve this insane bottleneck? How do you build an information superhighway inside a computer that's fast enough for what's coming next with AI? Because just trying to shove more electricity down those same old copper pipes, well, that's not going to cut it.
Well, the answer, and it's kind of beautiful, is to stop using electricity to move data and to start using something much, much faster, light. And this is where we introduce a technology called silicon photonics. Seriously, this is set to completely change how computers are built from the ground up.
The basic idea here is just so elegant. Instead of pushing electrons through tiny copper wires, silicon photonics guides photons, actual particles of light, through even tinier optical fibers that are built right onto the silicon chip. We're literally building data highways made of light.
And when you put them side by side, the difference is, well, it's not even a fair fight. On one side, you've got copper. Think of it like a clogged city street. It's slow, it gets hot, it uses a ton of energy, and you can't go very far. On the other side, you have light. That's the frictionless German Autobahn. It is massively faster, runs way cooler, uses a tiny fraction of the power, and can send data for kilometers. This isn't just an improvement, it's a whole new ballgame.
And the real-world numbers here are just staggering. We are talking about bandwidth that literally doubles with every new generation. A power efficiency gain that's more than 10 times better than copper. That means we can build bigger, more powerful, more complex AI models that use way less energy. This is how you scale AI for the future, sustainably.
Okay, so we have this incredible light-based technology. Fantastic, but how in the world do you actually build it? How do you connect these microscopic little fiber optic cables to a chip? Well, that takes a feat of engineering that's just as revolutionary as the photonics itself. It's a process called advanced packaging.
I absolutely love this analogy. It's perfect. If your AI chip is the Formula One race car, then advanced packaging is the elite pit crew. They're the ones who bolt everything on with microscopic precision, who manage the heat, who make sure everything is connected just right. In the race for AI, your pit crew is just as important as your driver.
And the number one strategy that this pit crew uses is called co-packaged optics, or CPO. The goal is super simple in theory. Get the little piece of hardware that turns electricity into light, the optical engine, as physically close to the main AI chip as you possibly can. By putting them right next to each other on the same package, the data's travel distance shrinks from meters down to just centimeters. That slashes delays and saves a ton of power.
And this is the star of the show. This is the optical engine. In this case, we're looking at TSMC's COUPE platform. You can think of it like a universal translator. It takes in the electrical signals from the chip, translates them into pulses of light, sends them flying down that fiber optic highway, and then translates them back to electricity on the other side. It's the bridge between two worlds.
So how does the pit crew actually do it? This flow here simplifies a process that is just mind-bogglingly complex. So first you make the optical and electrical parts, the dies, separately. Next, you assemble them into that optical engine and you test it to make sure it's perfect. Only then do you mount that verified, good-to-go engine right next to the main AI chip. And finally, you route these tiny, hair-thin fiber optic cables to it. It is a microscopic ballet of robots and insane precision. Now, a revolution on this scale, it's never the work of just one company. It takes a huge, interconnected, global ecosystem of specialists, all working in concert to bring this future to life.
And this diagram here, wow, it gives you just a tiny glimpse of how deep this supply chain goes. You've got companies that specialize in just the glass cores, others just for the heat sinks, others for the microscopic lenses, and of course for all the complex testing. It really is a global team effort.
And of course, leading the charge, you have giants like NVIDIA, and they are pushing this to the absolute limit. They're developing something called optics on interposer, which basically uses a silicon base layer to stack the optical engine and the electronic circuits in 3D, like a tiny skyscraper. It's a brilliant way to get them even closer together and squeeze out every last drop of performance. And this isn't some far-off dream. They're presenting papers on this for 2026. This is happening right now.
And it's not just the household names. You've got foundry giants like TSMC building the fundamental platforms, but then you have this incredible wave of innovators like Ranovis, IR Labs, and Celestial AI, and each one is tackling a different piece of the puzzle. Everything from slashing power consumption to creating entire photonic fabrics, they'll act as the nervous system for the next generation of AI.
So, where is all this headed? What does this roadmap to computing at the speed of light actually look like in practice? Well, it is happening a lot faster than you might think.
This roadmap lays it all out. By 2025, we're already hitting 1.6 terabits per second. Just a couple of years after that, it quadruples to 6.4. And by 2028, we're looking at connections going directly into our GPUs that are screaming past 12.8 terabits per second. To give you some context, that's fast enough to download the entire Library of Congress in less than a second. The speeds are just wild.
You know, it all comes back to this one really crucial point. AI isn't just another program that runs on a computer anymore. AI is the reason we are fundamentally reinventing the computer. It is the primary engine driving this entire trillion-dollar technological leap forward.
And that leaves us with one final kind of mind-bending question. We are building the physical infrastructure for information to move at literally the fastest speed possible in our universe. So once that bottleneck is gone, once our machines can communicate and think at the speed of light, what new frontiers will AI even unlock? What will it dream of next? It's an incredible